Hi, today we're going to look at problem 4 from the 2005 Form B AP Statistics exam. So let's take a look at it. A researcher believes that treating the seeds with certain additives before planting can enhance the growth of plants. An experiment to investigate this is conducted in a greenhouse. Um, and a large number of Roma tomato seeds, 24 seeds, are randomly chosen. So that's a good thing. You kind of see one of our first assumptions is met. We have some random assignment. And 2 are assigned each to each of 12 containers, right? One of the 2 seeds is randomly selected and treated with the additive. The other serves as a control. So in each sort of, I guess, little pot, there's 2 seeds, and one of them has this extra treatment on it that's supposed to make it grow better, that the researcher believes is going to work, and the other one does not. Both seeds are then planted in the same container, and the growth is measured after 30 days. And what you'll notice here, if we look at the data, we have the control group, which is the group of seeds that did not receive the enhancement additive, we'll call it. We have underneath that, we have the treatment group. This group of seeds did get the actual additive. And what you'll notice if you compare the means, the mean here 18.04 to the mean above it 15.989, that might lead us to believe that this treatment is actually causing a higher average amount of growth than just nothing at all. We have our standard deviations, and we even have our standard errors over here. Sort of fun when they give this standard error column. That's, you don't always get that output, but we know how to get standard error. We take the standard deviation and we divide it by the square root of the sample size. So if you wanted to confirm, that number is really the 1.175, which is here, divided by the square root of 12. And if you take a minute and put that into your calculator, we'll get 0.339. So that's sort of a neat thing. I'm going to confirm that actually right now while I'm talking to you here. 1.175 divided by the square root of 12. Yep, and it works. That's pretty neat. But in reality, in this case, you'll notice that there was an effort to match up the seeds. They put 2 seeds from the same type of Roma tomato plant into the same container, one with the additive, one with not. They were trying to create what's known as a match pairs design. That's what this is. This whole problem is a match pairs design. And the pairings are happening in each container. We're making sure that the seeds are treated the same, they get the same amount of water, the same amount of soil, everything about the way the seeds are being treated is the same, except for one has this additive and one does not. And so we look at this table here, the row we really care about is that last row. That last row that I've highlighted there is the information about the difference. And it actually did a lot of work for us. Typically, we have to calculate these things on our own, but we don't even have to today. For example, let's start to write some of this stuff down. So let's do that. So that we know that the sample size here in this experiment is n equals 12. We know that x bar of the difference is negative 2.015, right? So that's this number here. And then we know the standard deviation of the difference is 0.336. And I'm sorry, that's not correct. That, we'll get back to that. The standard deviation of the difference is 1.163. But ultimately, in these tests, we care about the standard deviation of the average difference, which is always the standard deviation of the difference divided by the square root of the sample size, which in this particular problem, they're really nice to us. They give us that number. It's that 0.336. So we're going to need these numbers later on in the problem. So part A asks us to construct a confidence interval for the mean difference in growth in centimeters of the plants from treated and untreated seeds. Be sure to interpret this interval. Now, when they mention to construct this confidence interval, you should go through the same set of steps that you go through if you're doing a significance test. So let's start to write a few things down here. So this is a one sample matched pairs T interval. And you should Start off with a let statement. Let mu sub d equal the mean difference in growth between treated and untreated seeds. Now, in any match pairs design, you need to decide what order you're going to subtract in. So if we look here, you'll notice that that difference they give us, let me highlight it for you here, is negative 2.015. So that means they took the control group up above, which is that, let's erase this thing now, because it's tough to see. But what it really means is they took that control group, that 15.989, and subtracted the treatment group to get the negative number that you see below it, the negative 2.15. So they're doing untreated minus treated. So we need to sort of come up with variables for this. So I guess we could just say let D, the difference, be untreated. So we can call that UT minus T, which is treated. This might not be the best use of variables, but whatever. That's what we're going to do. Okay, and then we go to our hypothesis. We don't have hypotheses here, but we could if we were doing a significance test. The next thing you want to do is check your assumptions. Number one, there should have been an SRS performed, but they mentioned that right at the beginning. We had 24 randomly chosen seeds, so that's a good thing. Number two, the population should be greater than 10 times our sample size, which in this case is 12 or 120, and that's true. And since that's okay, we can say that the standard deviation of x bar sub d is the standard deviation of x d over the square root of n. And we already had these numbers as 1 point. Let's go back up there. We had this 1.163 number, 1.163 over the square root of 12, and that turned out to be 0.336. And then finally, you're supposed to check for normality in some sense, or check that there's no skewness. And so what's interesting here is they don't give us a way to actually graph these differences, these data points. However, if you read carefully, there's a nice sentence in here. Graphical displays indicate the assumption of normality is not unreasonable. So in this case, they really sort of gifted us this last assumption. I could check that off and it works. And now we're ready to build our confidence interval. So here's how it goes. It's x bar sub d plus or minus. Now remember, the standard deviations we have in this problem are based on samples. So that means we use a t interval. So we're going to put t star. If we had the standard deviation of the population of all differences, then we would use z star. And then this is going to be times s of x sub d over the square root of n. If you wanted to, you could write this instead. You could write x bar sub d plus or minus t star times s of x bar sub d. These two things are really the same. Okay, and we actually have all these pieces if we go back to the original data set. So you'll notice here, there's a lot going on. So let me make this easier so there's no confusion. Let me just copy this. Let's go to a new page here. So just so we're clear, this number here is x bar sub d, and this number here is s of x bar sub d. So negative 2.1015 and 0.336. So we can plug all those in. Negative 2.015 plus or minus t star is going to be blank for a minute, and this is times 0.336. Now, in order to get t star, we need to know our confidence level and our degrees of freedom. So let's go back to the problem. Construct the confidence interval for this, and be sure to interpret this confidence interval. So you notice the confidence level is actually not given in this problem. So it looks like we have some leeway in terms of what we pick. So I'm going to go with a 95% confidence interval just because I'm so used to calculating that. If you were to look at College Board and what they accepted in terms of answers here, different confidence levels were acceptable. So if we're going to use 95% confidence, then what we do is we draw a little t distribution, which looks like a normal distribution. We mark off 0.95 in the middle. and we shade in this area, and we ask ourselves, how much area is in that tail? Well, it's 1 minus 0.95 over 2, which is 0.025. And also, our degrees of freedom in a significant t-test or a t-interval is always the number in the sample minus 1. So our degrees of freedom here are going to be 12 minus 1. Our degrees of freedom is going to be 11. So now what you could do is use a command in a TI-84 calculator called inverse T. And it always wants an area and it wants degrees of freedom. Those are the only two things it wants. And it'll give you back the T star you need. So to find that, you're going to go on your TI-84 calculator, you're going to do second vars VARS. You're going to go down to number 4, which is inverse T. It's going to ask you for that area, so we're going to put in 0.025. It's going to ask you for degrees of freedom, so we're going to put 11. I'm going to hit paste and enter, and we end up getting this. So when I get back, my T star that goes on this side is negative 2.201. So I'm going to put positive 2.201 here. This is a little plus or minus, so it wouldn't matter if you put the negative or the positive, actually. All right, so now that we've done that, we're actually ready to compute our confidence interval, or in this case, our 95% confidence interval. So if we do negative 2.015 plus 2.201 times 0.336, we end up getting an upper bound of negative 1.275. And then if we do the minus version of that, then we end up getting negative 2.75. Okay, so what can we say here? This is our 95% confidence interval. So we can say that we are 95% confident the true difference between the treated and untreated seeds in terms of growth is somewhere between negative 2.75, I guess it was centimeters in this case. Let's just make sure that's the case. Yep, growth is in centimeters, and negative 1.275. Okay, so when I look at these confidence intervals, I always think, all right, does it capture HO or not? Does it capture 0 or not? So in this case, we look at part B. Part B says, based only on your confidence interval in part A, is there sufficient evidence to conclude that there is a significant difference in the mean growth? All right, so I would look at this confidence interval, and I would notice, sorry about that, screen jumped for a minute. I would notice that the following: 0 is not in the interval. And therefore, 0 is not likely to be the true mean difference between, actually difference in growth, I should say, difference in growth between treated and untreated seeds. So remember, in our case, in this problem, we did untreated seeds minus treated seeds. And this researcher expected these guys to have less growth, which would imply that this difference should end up being negative. And what we found out with our confidence interval is that we think the true difference is somewhere between negative 2.75 and negative 1.275. So if we think that the true mean difference of untreated versus treated is somewhere between these two negative numbers, that means that the true difference between them is probably negative, which means most likely the untreated seeds have less growth than the treated seeds. And that would give us some reason to believe that this treatment that we're applying to the seeds is effective at the 95% confidence level. Okay, great. Thanks for watching.